Hello, and welcome to a further tutorial for Exudyn. This time we are looking at a mass spring damper tutorial in a very basic manner. So in order to get started, I created a new file. I'm using Spider Python 3.11 and Exudyn version. So let's see this. We just run that and then we see version 1704, and with any newer version you will be fine. Also with 1.7 it should work fine. Now in order to get started, we also import NumPy. Usually with Exudyn, some packages required. So NumPy is always required, but some packages require SciPy. Some sub packages require, of course, matplotlib for plotting. We need PyTorch for machine learning. So many packages then will just show up as soon as they are needed, or MPI for Pi, for example, for MPI parallelization. Now, the next step is to create again a system container, as in the basic tutorial. So we create a system container and we add a system. So with that, we first get started. And now we set up some basic parameters for the spring damper example. So before I continue, I mean, this example is in the tutorial. So if you go to the read the docs and then you go to the tutorial section, and then there's several tutorials, and the second one is the first one is the mass spring damper tutorial that we are going through now, and it's described term by term, so you can also just read it there. We start with say some basic dimension: length 0.5 meter, mass of 1.6 kilogram. Let's add some comments here. Then we have a spring with 4,000 Newton per meter, and a damping which has 8 Newton per meter per second. We also will use some initial velocity of minus initial displacement, sorry, minus 0.08 meter, and the initial velocity of 1 meter second. And so that is in the good shape. And we will add a force of 80 Newton at the mass that we are investigating. And the static displacement, we can immediately compute it, and it would be just force divided by the spring stiffness. So the whole mass would then be just subject to the force, but there will be no gravity or something. And so I will just print the resonance frequency, which is just the square root of spring stiffness divided by mass. And we can also print deflection, which is just the x0. So doing that, we can just run it, and we see resonance at 50 radian per second, and the static deflection of 2 centimeter. Now let's create the model. And for that, we're doing it here with the very basic way. So there's simpler create functions. as you have seen in the basic tutorial, but here we will really work with the nodes and markers and everything that is underlying. So we will start with a node, and the node is of type node point. So it's a three-dimensional point, and it has reference coordinates L00, and it has initial displacements or coordinates, in this case u0, 0, 0, and it has initial velocities of v0, 0, 0. You might ask why it's not initial displacements, but it's kind of consistent with most bodies that we have rotations and displacements, and that's why it is coordinates for consistency. We then add also a ground node, which is a node that is always fixed. So call it in ground. So again, as in the basic tutorial, what we get here back from add node is a node number. Yeah. And so we add another node, and this now is a node point ground, which is a node that is fixed, that cannot move, has no unknowns, and it just gets a reference coordinates, and we use 0, 0, 0 here as a reference point, where we can attach now the spring. Now we add the mass point of the type body, which is really not a mass that we want to move, and we can use like some name sorted mass point and add an object mass point, and this one gets a physics mass, and this is now defined before mass, and it would have a node number, which is now the n1 that we defined. And yeah, it could also have some visualization, but we right now in the tutorial don't add any visualization. So what you might also have seen here is that as soon as we just start to open bracket here, we see that it's not saying mass point, it's saying object mass point. So some of these things have abbreviations, like the point is in fact a node point. So do it this way, it will show us this is a node point, but we have an abbreviation point because yeah, it's just simpler to write. And the same is for mass point. Okay. Now, as we have all the objects, they would freely move in space. And so we want now to create a spring between the two nodes. And in fact, just between the two x coordinates. And for that, we need markers. So we add a ground marker. And the ground marker is, in this case, just a marker node coordinate. And this would work with a node number, which is in this case n ground. And it would add a coordinate. And for this now, in fact, it doesn't matter what we use here because the ground node has no coordinates, and whatever coordinate we would like to attach to the marker, it would always give us 0, which goes, this ground node cannot move, which means the coordinate is always measured to be 0. This is different from the let's say marker n1, which is the marker for the node n1. We can just copy this one. And here we have node number n1, and again, a coordinate. To measure, we use the coordinate 0. So it measures the x coordinate now. And in order to attach any kind of connectors or constraints, we can only attach them to markers. So what we do now is to use a coordinate spring damper. There would be many other options as well. We could use a Cartesian spring damper that would act directly in the nodes, but here a coordinate spring damper operates on coordinates like an x coordinate or y coordinate, a rotational coordinate, whatever coordinate you have in your system, you can attach a coordinate spring damper and a coordinate marker to these coordinates. So now we insert here the marker numbers, which is the ground marker and the marker N1. And we also define now some stiffness, which is the stiffness we defined before, was the spring, and some damping, and this was before the, if I remember correctly, the damping. Okay. And with that, we defined the coordinate spring damper. We also wanted to have a load attached to that. So, but we don't need it anymore, so we don't store this now. So we say we take a load coordinate, which is a load on a coordinate. We could also add a load on a point node or on any point in a body, but the coordinate would again act only on a x or y coordinate. So if we supply now the marker number, it's just one, the node marker, we can add a load to the load marker. And so we can just say a load, which is now a scalar quantity, I call this f. This would be applied to this marker. Finally, we add a sensor to measure the force, let's say. So, but we can measure any other quantity that is available. So we can measure the displacement of the mass, or we can measure velocities, accelerations, forces, whatever. And for this object, we need now the object number. So that's now called NC. But I should call this for consistency coordinate spring damper. So let's call this OCD. And we can either now output this to the file, or we could say store internal, and then this is just stored internally in memory. And we have to supply the output variable type, so we have to say what is measured. And for that, there is like different types, output variable types, and we just want to store the force for this spring damper, which is the force that is measured by the spring damper. We can do everything, put everything together. I just did some typo here. So the mark. Okay, so we have to do this. This was in the tutorial. Now this runs, and we can just say print MBS, and this would show us the basic data we have: two nodes, two objects, which is the coordinate spring damper and the mass point. We have two markers defined here, two nodes, ground node and the node N1. And we don't have any coordinates assigned to the system. So why is this? Because we didn't say so far number. We can do this again and run it. So pressing F5 or the play button. And if we print again the MBS, we see now we have three ordinary differential equations. Second order, which is the x, y, and z coordinate of the mass point that can move. And now we can simulate. So let's say we simulate it for 1 second. information is sometimes annoying. So then we use some step size, let's say 1 millisecond, and then we create again simulation settings, and we adjust some things here. So we can see the time integration of steps equals t end divided by step size, and the end time is t end. We do a couple of things to add some visualization of the output. We can also do some things like to display some statistics and some measuring of time if you are interested in the timings. And there's some more things set in the tutorial file if you open it. And we also can adjust the visualization settings to see them as. So let's say the nodes again. We draw them as a sphere, and we can also adjust the default size, which is then 0.1, and then we will see a nice representation of this mass. Here we will now immediately start the renderer. And in order to do not start immediately with simulation, we will wait for pressing space. And then we start the solver, solve dynamic, with the simulation settings. Using the default solver, and then we just say stop renderer, and before that we can say wait for render engines stop flag, which means that we wait until the user closes the window, otherwise it will close automatically. And finally, we can visualize some results. So first we can just print the or measure the final position of node, the X position. So we just say mbs get node output of our node. It was now n1, and the variable type equals x output variable type. So dot position. And we could measure this in any configuration, like in the visualization or in the initial configuration, but we just use the default, which is the current configuration. Now we can just print it, and it would give us this displacement. And let's see now, we see this system. One is the ground node, the other is the moving node. We could have used different ways to draw it. It of course simulates very fast, so we don't see any results directly here, and it then writes us all these outputs. It splits up the computation time, and it would write the final position of the mass point, which is, let's say, after 1 second, undamped. And we could just increase this time and also avoid this computation time. Run it again, and then it should yeah, it will go now to this position, which means that it was initially starting at 0.5, but as we have a force attached, with a static deflection of 0.02. So it has to move to 0.52 meter, and it does it exactly after this time. So let's reduce this a little bit again. And in order to see what happens, you could just run the solution viewer. I will just run this line now with F9 in Spider, and this would load now the solution, and it would show us again, as in the basic tutorial, the behavior, and we see the damped oscillation of this mass point. And we could also, let's make it a little bit shorter here, and with this, we could also again plot the sensor output, and there's a deep interface here, but we can just do it for the sensor we've chosen, which means if we save this sensor as a default and we use it here as an input, and let's now turn off this waiting. We can just start it. It will just open and close again. And it will then plot our damped solution, and you see here the damped oscillation. You can adjust the amount of output from the simulation. So this was a little bit low resolution, so we can adjust this as well. So simulation settings, solution settings, sensor right period, and we just take here the same as the step slide. So every step is now written to the sensor. And yeah, I did something wrong here. It should be this way. And then let's run it again. And then we can zoom in, and we will see that it's now much smoother solution because we output all the steps. And yeah, in the tutorial, you would also see then a more detailed analysis of the solution and the comparison with the exact solution, but we will not do this here now. There's just one thing that might be interesting because sometimes we would like to add other loads, and so I will do the following. Instead of having this load F, we will use a load user function, which we call UF load, user function load, and we have to define it previous to the usage of this function. And this is a function that has to return a scalar force. In order to find out how this really should work, we just go to the load coordinate object. So let's go to the read docs documentation, and here we have the load coordinate. And then there's the load user function, and if we go down a little bit, then there would be, usually at least, the description of the user function. See, yeah, here it is. So it tells the multi-body system, you get it into the function, the current time, and the load as you, oh, sorry, and the current, the load that you specified in the object. Now, the return value should be just a scalar, the computed load, and it looks like that. So we can, in fact, just copy from here. We have a user function load, and we would like to return, let's say, sine 10 times 2 pi t. And let's see, maybe we use a little bit larger amount of force. So let's take maybe this one, or even larger than that. Let's take 100. And so it would be a 1 Hertz oscillation. Let's take a 2 Hertz. And with that, we simulate it again. And we would see now that there is some error. Let's see where it went wrong. Yeah, clear. So we have to use force here, or we have to change this to load. Just following the sign is usually not defined in Python, but in the Exudyn utilities, sign is included. So let's check sign is defined, but it is already here. So now it should work. Yeah. And no, that's not a big difference to the previous one, but we see here now that we have this additional oscillation, and let's check if we remove now the initial coordinates and the initial velocities, if we now get this yeah, this was wrong. Should put it here. Yeah, that was a mistake. It shouldn't be 100 here. It should be here, or the load. Let's take it again. Now it's what we get. Yeah. So now we have the force that is applied, which is again 80 Newton, and after some initial oscillations until the damping is reached, we get these force values, and maybe we can do it a little bit improved. We could just add the sensor for the position. Let's call it center pulse, and this would now measure the position, but let's say displacement, because the Cartesian spring damper wouldn't have a position, it would have displacement. We can also check this one. So take the coordinate spring damper, go again to the documentation, and then look at this object. So it's a connector coordinate spring damper, and if we go there is connector forces, and there should also be the output variables. So it's displacement, velocity, and force that you can measure. So the displacement should be well available. And now we can also plot then the displacement now. The displacement, let's say, of the connector. This simulated is given here. So it's like approximately the static displacement, because we have a rather low frequency oscillation, but of course it's a little bit different from the static displacement due to dynamic effects. And we of course see the initial effects starting from standstill. So with this, I think you got some idea how this works in Exudyn with user functions, coordinate spring dampers, markers, loads, nodes, objects, and so on. And with that, you could create much more complicated models. There are two further tutorials then to come, one on rigid bodies and another one on beams. And I hope that you will also watch this one. So thanks a lot for watching, and see you next time.